Good afternoon, everyone. Greetings from Department of Civil Engineering, Vidyavardhaka College of Engineering, Mysore. I am Madhushri C, Assistant Professor, Department of Civil Engineering. Welcome everyone for this day 8 sessions of GATE 2021 online training program. We have two sessions which is scheduled today between 2 to 3:30 by Professor Dr. S.K. Prasad on Foundation Engineering, and the second session on solid mechanics by Professor Dr. Umesh P.K. Tomorrow at between 11 to 12:30, you will be having session on engineering mathematics by Professor Shweta. Please tune in tomorrow between 11 to 12:30 for mathematics session. So with this, I would like to welcome or introduce today's speaker for session 1 on foundation engineering, that is Dr. S.K. Prasad. Dr. S.K. Prasad, Professor and HOD, Department of Civil Engineering, BBC, Mysuru. Born on 26th February 1960, he obtained his BE in Civil Engineering from S.J. College of Engineering, University of Mysore. Masters in Geotechnical Engineering from IIT Kanpur. Doctoral Engineering in Earthquake Geotechnical Engineering from University of Tokyo, Japan. He is a recognized reviewer for Indian Geotechnical Journal, Canadian Geotechnical Engineering Journal, International Journal of Geotechnical Engineering. He is also the member of Quality Control Cell of Karnataka and Army Corporation, Mysore. He has actively taken up consultancy works in the field of geotechnical engineering. He has organized many short-term courses to working professionals from KPWD, KID, and KLAC, KPC, etc. on topics of geotechnical engineering, structural engineering, and computer applications in civil engineering. With this brief introduction, I would like to welcome our beloved HOD, Dr. S.K. Prasad, to the session. Over to you, sir.
Thank you, Professor Madhushri, for the nice introduction. And good afternoon, everybody. It's always a pleasure to, speak to the participants. I have always been doing it for the last 35 years. And I feel very proud and happy that, my department here in Vidyavardhaka College of Engineering has started this unique program of training, those who are aspirant of GATE. So we want to continue this, in the years to come. And I want every one of you to take the advantage of all these things. Basically, knowledge is something which we have to, acquire continuously. And anybody interested in learning more and doing well in life, have to be very competitive in that respect. Whether you want to take admission to postgraduate education or not, taking GATE is always advantageous. Well, I will be speaking about foundation engineering, 2 sessions. My colleague, Professor Chetan, has already spoken about the fundamentals of soil mechanics, 2 sessions. And there is quite a vast subject here to deal with, but I'm not sure how quickly we can cover. But I tell you here, the focus is not on concept alone. The focus also is on how to crack GATE problems. And as I have noticed, the questions in GATE examinations are relatively slightly indirect, and whatever you deal with in examinations, compare them with the questions here. You will have to understand the question very well. You'll have to read the question paper, maybe not just once, and you take some time in understanding, especially in geotechnical engineering. Most of them are problem oriented. There are areas in which you'll have to remember some formulae, and you should know how quickly you can handle. For example, any question in GATE which carries 2 marks may perhaps carry 6 to 8 marks in a conventional examination. That means, you have less time to analyze, and in that less time, you'll have to achieve your goal. I really was impressed with the first day's introduction, which my colleague, Professor Chetan, gave. He made this statistical analysis, and then he showed that, according to Pareto principle, you can possibly achieve the best by focusing on some very clever and smart way of understanding and taking, putting in effort in one particular direction. He said that 80-20 or 20-80, whatever rule. So you can possibly, do 20% of the work, but still achieve 80% of the results. So that principle could definitely be applied to, your learning for GATE also. See, basically, whatever you are doing in GATE is something which you have already learned in your undergraduate career. So you only have to brush up and in a best way. So here, if you understand that some of the topics are hot from the point of view of question paper setters, then focus on them and you'll be able to achieve the best possible results. So if you apply the same rule, 80-20 rule here, just by taking 20% of the total syllabus, you still will be able to crack 80% of the efficiency or result. So keep that in mind. It could be 80-20, it could be 70-30, or sometimes 60-40, but be smart in preparing for GATE. And the other thing he mentioned is that there is no shortcut for any success. And here, if you want to succeed, you'll have to put in sincere effort. So hard working is important. I say along with hard working, smart work also is equally important. Take that. He made a good statistics of how GATE questions are covered from 1991 till date. So naturally, statistics plays an important role in giving some idea about how the background is and how the mentality of the question paper setters is. And interestingly, you will notice that from the point of view of geotechnical engineering, okay, this is any GATE examination is very hot in the sense, maximum questions come from geotechnical engineering. Keeping that in mind, and also understanding that geotechnical engineering covers 2 courses which you do in your undergraduate career, possibly one in 4th or 5th semester, another in 5th or 6th semester. One textbook is sufficient. If you thoroughly understand that, then to crack GATE examination, at least to crack geotechnical engineering in GATE examination, you should not have much difficulty. And if you do that way, you are very sure that you will approximately get about 15% of the marks, and 15% marks is not a small amount in GATE. And so if you take any other discipline, say structural engineering, you may have to study more, much more vast syllabus is there. So put in good effort in geotechnical engineering. And so he made an analysis since 1991 till date. Maximum marks is allocated to geotechnical engineering. So the next highest is environmental engineering, which falls much behind this, almost 60-70% of geotechnical engineering. Keep that in mind. And also he made another analysis and said that the topics covered in geotechnical engineering, which involves soil mechanics and foundation engineering, have marks allocation something like this, where most of the things coming in soil mechanics will have a lot of emphasis. But interestingly, what I will be covering in foundation engineering, shallow foundations and bearing capacity, has maximum marks allocated, which means, examiners would like to give questions in that area. So there is every possibility that, even this time you have the same kind of trend, like, retaining wall, deep foundations, stability of slopes. So I'm not sure how much I'll be able to cover today, but these are the portions. What you see on the right side are the portions which I'll have to cover. And I'll be spending my next lecture on foundations, both shallow and deep foundations. I'm hoping that I'll cover these 4 topics today, and I'll have to see how much I'll be able to cover. So these are the syllabi from foundation engineering. As I said, subsurface investigation, earth pressure theories, stability of slopes, and stress distribution in soil. Okay, along with the topics related to foundations, both shallow and deep foundations, including settlement analysis. I'm taking earth pressure theories first because that's one thing which has more emphasis by the question paper setters. And there are many researchers who have worked on earth pressure theories, but two classical ones we always talk about are one by Coulomb and another by Rankine. Coulomb gave his theory much before geotechnical engineering started getting recognition. We say that geotechnical engineering started getting recognition from the point Professor Terzaghi came into being as a professor in soil mechanics. So in 1776, Coulomb gave his theory, and followed by Rankine about 80 years later in 1857. Okay, I'll start with Rankine's theory because it is more analytical, unlike Coulomb's theory, wherein you prefer to use graphical method. So he made a number of assumptions. Unless you make assumptions, you cannot formulate theories. And especially in geotechnical engineering, where a lot of complexities are involved, you need to make many assumptions. And some of the important assumptions which we generally make in soil mechanics are, soil is isotropic homogeneous, which never is the case. And in this case, soil is considered to be cohesionless while deriving, but then, you are adding the effect of cohesion in an indirect way. And it is planar. Basically, it's planar. Therefore, you may be able to represent the problem in two-dimensional plane strain situation. Therefore, even the failure surface is also considered to be planar. And how accurate is this assumption? Very difficult to say. But then, this assumption gives us an opportunity to make our theory relatively simple. And the failure wedge is a rigid body which experiences translation. So it experiences only one mode of movement. Back of the wall is considered to be smooth. Strictly, it will never be smooth. But then, once we consider it smooth, we can avoid the friction between the wall and the backfill soil. Likewise, I said that it is a plane strain problem by assuming that, we can convert a conventional, regular three-dimensional problem into two dimensions. Basically, this theory is based on the failure criteria, more Coulomb. So you all know at the instance of failure, more Coulomb failure criteria gives this expression. You should be very familiar with this expression. So entire theory of lateral earth pressure is based on this expression. What does it say? Sigma 1 and sigma 3 are the major and the minor principal stresses. An element of soil or an element of material which is under more Coulomb criteria, okay, experiences. Sigma 1 is the principal, major principal stress. So, and sigma 3 is the minor principal stress at the time of failure. And then you have two things, the shear parameters, the strength parameters C and phi represented this way. So C is cohesion, which comes here, and phi is embedded inside this expression alpha. Alpha represents 45 plus 5 by 2. So this is very simple. It can be easily derived, and I want you to remember this. And why do you require earth pressure theory? Because, in any construction, there are many areas in which you'll have to store earth at two different levels. So on one side, it is at a higher elevation. On the other side, it is at a lower elevation. It can happen in, large embankment kind of structures. It can happen in underground structures. So you need to hold soil at two different levels. And soil is a very special material, particulate. It just cannot stand by itself vertically. And for you to make it stand vertically, you will have to think of some indirect method or build a wall. And when you build a wall, automatically the wall will be subjected to a pressure, a horizontal pressure by the earth behind it. And we have to estimate, assess how much is that pressure, at what level the resultant of that pressure acts, and we should be able to design that structure, that is, design that wall to take care of that. So from the point of geotechnical engineering, broadly, we consider 3 earth pressure criteria, 2 extreme cases of failure, and 1 earth pressure at rest. So earth pressure at rest state, active case, and passive case. These are the 3 cases which are considered. So you take a wall, okay, which is holding the soil at this level on the right side, at this level on the left side. If I remove this wall, soil cannot stand by itself, it will fall down. And hence, this wall is subjected to horizontal pressure. Then you have 3, specific situations coming into picture. One is an element of soil is not subjected to any strain, any lateral movement. The soil is at rest. There is no strain. That we call as earth pressure at rest. So absolutely wall and the soil behind it, which we call as backfill, or at stationary position without anything happening. For that to happen, there is some force which the soil will exert onto the wall. And this wall should be designed to take care of that. The other 2 cases are 2 extreme cases. At both these cases, that is active and passive, the structure will fail. That means the wall will fail. Wall will fail because the soil behind will have a lateral movement, will have a movement along the failure surface. One extreme case we call as active case, when the total weight of the soil will push the wall away from itself, away from the backfill portion. And in this case, it is the weight which is responsible for failure. Therefore, sigma 1, that is major principal stress, is that weight. And hence, sigma 3 is that stress, that extreme stuff which happens, and that is the lateral stress which we will have to evaluate. This value will be much lower than what you have at rest condition. On the other hand, you also can make the soil here fail by pushing the wall towards the soil. And for that, you require enormous amount of force. You push in such a way that this force is much, much bigger than the weight itself. Therefore, sigma 1 is horizontal. Major principal stress is horizontal and sigma 3 is vertical. So this situation we call as passive situation. So wall moves away from the fill in active case and wall moves towards fill in passive case, which also can be explained through a graph between the lateral pressure and the lateral strain. Please note that earth pressure at stress will involve no lateral strain. On the other hand, I call this side as positive. That means, when the stress is happening, when the movement is happening away from the wall, and that I call as positive. And this will induce a, this amount of maximum lateral strain, and the corresponding lateral pressure is this much. This we call as active earth pressure. And at active earth pressure, this is the amount of strain the soil will experience. On the other hand, the passive earth pressure is this much. The passive earth pressure which you can compute is this much, and this will induce a much bigger lateral strain equal to this much. So up to this much, okay, the soil is said to be free from failure. Whenever it reaches this point or this point, there will be failure. So if you have designed in such a way that the amount of strain happens within this region, the structure is safe. So whenever you design a retaining wall, whenever you are designing a cellar floor, okay, whenever you are designing a swimming pool wall, wherever you have the earth on one side, you have to see to it that strain is within this. So many a times when we design, we take this extreme situation. Sometimes we take this situation also, which is very safe. Actually, you don't want any strain to happen. So you take a situation when you have earth pressure at rest condition. Okay. So with this, I go on to active earth pressure to start with. That is the most important thing from the design point of view. Many a times you will also have to satisfy passive condition, but this is what you do. And basically, the things which you calculate are, I put it as small PA. It is the intensity of lateral active earth pressure, the maximum value at any point you want to know. Okay. And then using this and using the other details, you try to find out the total thrust, total active thrust. I use the symbol capital P suffix A. And at what position in the body of the wall the resultant is acting. Resultant, that is the total thrust, is considered to be acting. That is also required because you need to find out the moment from that and so on. So these are the three things which we try to determine. And for horizontal top surface and back of the wall vertical, so that is the simplest case. Considering that, we try to apply it to the other situations. Very quickly, I try to go on to different situations in earth pressure. So I'm considering the simplest case. You have a wall, smooth vertical wall. You have the soil horizontal along the backfill portion, horizontal soil, and this entire soil is homogeneous. And in active situation, please remember sigma 1 is vertical, sigma 3 is horizontal. I consider any element at a depth z below the top surface of the soil, and note that in active case, sigma 1 is bigger than sigma 3, or in other words, the vertical stress is bigger than the horizontal stress. You need to remember that if you have water or any fluid, then the stresses are uniform both in vertical and horizontal direction. The particle of water is isotropic at any depth. That means, if you consider at some depth, let us say 1 meter depth, water, okay, water is approximately having a density of 10 kilonewton per meter cube. So at 1 meter depth, the pressure will be 10 kilonewton per meter squared, both in the vertical direction as well as in horizontal direction. In case of soil, which is always very peculiar, particulate in nature, at 1 meter depth, if I assume that the density of soil is 20 kilonewton per meter cube, then the vertical pressure will be 20 into 1, 20 kilonewton per meter squared. But the horizontal pressure may be either less or more than 20. In one extreme case, that is in the active situation, horizontal stress will always be lower than the vertical stress. So if it is 20 kilonewton per meter squared, the vertical stress, the horizontal stress at failure will be less than that. And how much less depends upon the properties of soil. It depends upon the density of soil. It depends upon the strength of soil. And that is what we are going to see. So I use this formula and I'm considering for convenience, cohesionless soil, therefore C is automatically 0. Then sigma 1 is equal to sigma 3 tan squared alpha. Sigma 1 is the vertical stress. Very easily you can determine that is gamma Z. Gamma into gamma, which is the unit weight of soil. I'm assuming it to be homogeneous. Therefore, gamma happens to be the bulk density of soil. If it is saturated, of course, you'll have to consider the effect of water also. We'll come to that. So bulk density of soil. So gamma is the density of soil and Z is the depth at which you are considering to determine the value. Sigma 3 happens to be the lateral pressure, intensity of lateral pressure. I'll say small PA for that. So gamma Z is equal to small PA into tan squared alpha. I go to the, that's what I'm saying. Sigma 3 is horizontal, that is small PA. C is 0. Alpha is 45 plus 5 by 2. So if I apply here, gamma Z is equal to PA tan squared alpha plus 0. Or PA is what I want to find out. The intensity of earth pressure is equal to gamma Z by tan squared alpha or gamma Z cot squared alpha. This cot squared alpha is represented as a coefficient of earth pressure, and in the extreme situation this K is Ka, that is coefficient of active earth pressure. So cot squared alpha is equal to Ka, which also trigonometrically you can call cot squared 45 plus 5 by 2 is as equal to 1 minus sin phi by 1 plus sin phi. If phi happens to be the angle of internal friction of soil, then Ka, that is the Rankine's coefficient of active earth pressure, is equal to 1 minus sine phi by 1 plus sine phi. Or it is simply cot squared of 45 plus phi by 2. Therefore, the active earth pressure going back here is equal to Pa is equal to Ka gamma Z. I want you to remember this. So, active earth pressure, yeah, will be like this. And then, where will it be maximum? At Z equal to 0, active earth pressure is 0. And at Z is equal to H, active earth pressure will be Ka gamma H. So it is triangular. Okay? And hence, the pressure intensity is 0 here and maximum here. So resultant total pressure will be simply the area of this triangle, which is equal to half into the intensity of pressure multiplied by height, which is, I call it as capital PA. Capital PA happens to be the thrust, total active thrust. And where does it act? Because it is triangular, it acts at a height h by 3 from the base. And PA is equal to Ka gamma h squared by 2. That's what I have put here. I want you to remember this. And this basic fundamental formula you should all have in mind. So then, I keep on applying some additional features to it. In the earlier case, I had considered a situation when there is no surcharge at the top. There may be surcharge due to some structure acting on it. There may be surcharge because of the overburdened soil above it also. So if there is a surcharge of intensity Q, then you have the original triangular loading due to the soil behind the backfill, and you also have a rectangular loading due to the surcharge, which is equal to, magnitude wise, Ka times Q. Ka happens to be the property of the soil. That is the coefficient of active earth pressure, which is equal to 1 minus sine phi by 1 plus sine phi. And here it is Ka gamma h, which is triangular. So you need to consider this plus this. So whenever there is a surcharge, please do consider this additional earth pressure, which is equal to Ka-Q. So always the effect of any surcharge is to increase the earth pressure. And that surcharge is going to have uniform value both from top. So your PA will now be a combination of these two, PA1 plus PA2. PA1 is the case which I mentioned in the previous case, Ka gamma h squared by 2. And PA2 is the effect of surcharge, which is Ka into Q. And where does it act? It is just, your basic fundamentals of mechanics. Triangular load, the resultant will be at h by 3 from the, base, or 2h by 3 from the apex. Whereas a rectangular one, the resultant will be at the center. So the resultant for these two will be within the combination of these two. We'll have to work out just using the mechanics principle. Now I consider the next case where you have a submerged backfill. I always say water is the worst enemy to a geotechnical engineer. Whenever water is there, it makes things complicated. In general, water will reduce the strength of soil. In addition, it has its own peculiar way of acting. So what we do here cleverly is, as per Rankine's theory, we separate out the soil effect and water effect. So soil particles effect we take from gamma submerged. Whereas water effect, I already told you, water or any fluid has horizontal thrust, same as the vertical stress. K, coefficient of pressure, is going to be unit 1 for that. Whatever is the vertical pressure, same is the magnitude for horizontal pressure also. Therefore, I have separated out the soil effect, and hence, it is Ka. Please note gamma sub. Sometimes we use gamma dash also for this, don't get confused. Gamma sub or submerged density into H. Plus, I also need to consider the water effect. K for water is 1, therefore I am not putting K at all, gamma IW into H. You need to consider these two, and hence you have a triangular load, and correspondingly you know that the total active earth pressure will be equal to the area of this triangle. That is when you have a submerged backfill. You also may have an inclined surcharge. Whenever there is an inclined surcharge, the earth pressure is going to be high. You have a situation when the inclination increases, earth pressure is likely to increase many folds. And hence, when you are talking about a retaining wall in a hilly terrain, you have to be extremely careful. There have been many failures because of wrong understanding of the earth pressure in these cases. You need to actually consider this effect. And for that, you have a big formula. I wouldn't advise that you should remember this formula, but you should know that in Rankine's theory, we assume that the resultant active earth pressure is also proportional or parallel to the the surcharge inclination. So it is inclined at an angle beta. You calculate PA, that is total thrust, the same way you calculate for the other case. But Ka is not going to be just 1 minus sine phi by 1 plus sine phi. You are using this formula, which is a function of not only phi, but also beta. You notice that when beta is 0, this will reduce to that same formula, 1 minus sine phi by 1 plus phi sine phi. But when beta increases, this value increases enormously. That's what you have to take into account. And hence, you have a triangular load, something like this. Then you also have a situation when the wall is not vertical. If the wall is not vertical, you have a triangular wedge of this backfill which will be carrying this extra load. So what we do is we consider the weight of this. You calculate PA1 the exactly same way as you have for vertical load. Then you consider these two forces, one vertical force, another horizontal force, and find the resultant of these at whatever inclination you get depending on this angle alpha. So that's the only correction which you need to apply. And this is all about the earth pressure theory with respect to cohesionless soils for active case. So then you have the cohesive soil. In cohesive soil like clay, to some extent silt, you need to consider the effect of cohesion, which is one of the other shear parameters. So here you consider C also. So PA now is no longer only a function of phi, but PA is equal to gamma z cos squared alpha minus 2c tan alpha, because this goes to the other side. So what does it mean? Effect of cohesion is to reduce the lateral thrust. So if you have a cohesive soil, maybe it is able to stand by itself for some height. And at the top, there is a likelihood that there will be some amount of tension. So that's what you have to keep in mind. So PA is equal to gamma z Ka cot squared alpha is Ka minus 2c times root of Ka. And Ka, 1 minus sine phi by 1 plus sine phi. So as I said, all these are positive thrust pushing the wall. But at the top, you have tension. Wall moves, the soil, backfill soil, moves away from the wall. It reduces the stress. So this is on the negative side. Therefore, sometimes we try to find out till what height this soil can stand without the wall. Naturally, this is negative. So this total will be equal to earth pressure 0. So if I can find out Z naught here, HC is simply 2 times Z naught. And this is negative minus 2c root Ka. How did I get it? Because, at Z is equal to 0, this is 0. Pa is minus 2c root Ka. And this value Hc, very easily you can show that it is equal to 4c into root of Kp. Please note, Kp is the, passive coefficient of passive earth pressure, which is reciprocal of Ka, which is equal to 1 plus sine phi by 1 minus sine phi. Kp is cot squared alpha Ka is cot squared alpha, Kp is tan squared alpha. Okay, so 4C into root Kp by gamma. I want you to remember this. So effect of clayey soil is to reduce the earth pressure, and the quantity cohesion, if it is more, it will be able to stand, the soil will be able to stand vertically for longer distance. Somehow I want you to remember this or quickly solve using this formula. Okay. So passive earth pressure, very similar to active earth pressure, but the other case in which, the horizontal thrust is bigger. Sigma 1 is the horizontal stress, stress, whereas sigma 3 is the vertical stress. So in this case, sigma h is greater than sigma v. So if you apply the same formula at the time of failure, in this case, sigma 1 is sigma h, which is pp. Sigma 3 is the vertical stress, which we gamma z. Substitute, and hence, you find pp equal to reciprocal of, kp equal to reciprocal of ka. So 1 plus sine phi by 1 minus sine phi. Or kp is equal to tan squared alpha, tan squared 45 plus 5 by 2. So exactly when I apply the same rule, it will also be triangular, but this is kp. Kp is a much bigger value, greater than 1. If phi, on the other hand, when phi is equal to 30 degrees, ka is equal to 1 by 3. Okay. So 3 and reciprocal of 3 is 1 by 3. So passive earth pressure, total thrust will be equal to kp gamma h squared by 2. So basic limitations of Rankine theory is that, you assume that wall is smooth. You don't consider the roughness of the wall. If you consider roughness of wall, then automatically you need to consider that extra force, that frictional force, which is not considered. And, cohesion is indirectly used here. It is not explicitly defined. So I'll very quickly take up a few gate problems. You'll have to read this properly. Consider a rigid retaining wall with partially submerged cohesionless backfill with a surcharge. Please note, whenever there is a surcharge, what is the best pressure distribution? Please note, without surcharge for homogeneous soil, the pressure distribution is triangular. For surcharge, you consider rectangle. As I told you earlier, rectangle plus triangle. Therefore, B is the best possible solution. It is not A, it is not C, it is not D. Therefore, very quickly you should be able to point out that it is B. Again, you'll have to read it, it takes some time for you to read. That's why in examination, gate examination, I want you to read the question thoroughly, especially in geotech. The phrasing is too lengthy. You have a retaining wall of height h with a smooth wall. Whenever it is smooth wall, Rankine theory can be applied. And it has a backfill which is inclined at an angle beta with respect to horizontal. The backfill consists of cohesionless soil only, having internal frictional angle phi. If the active lateral thrust acting on the wall is Pa, which one of the following statements is true? I take the first one itself, which is the answer. Please note, the total thrust, I already told you, whenever you have a inclined backfill, the total thrust will also be parallel to the inclination. So it is also beta. And this triangular, this distribution is triangular. And hence, the location of the thrust is at h by 3 from the base. So Pa acts at h by 3 from the base of the wall at an angle beta with respect to horizontal. This is the correct answer. So here it says it acts at h by 2. Here it says that h by 2 and angle is not beta, angle is phi. Here it says it acts at h by 2, but angle is beta. Here it says it acts as h by 3, angle is phi. So very easily you can eliminate B, C, D. Therefore, A happens to be the right answer. I want you to be careful with this, question. Most of the times you get a question like this, 2 marks. A 8 meter, I want you to very quickly write down the sketch. Okay, I have made a mistake here. I have put here as 3 meters, it is 4 meters. A 8 meter high retaining wall has smooth vertical back face. Okay. Top 4 meter is made of the first soil, whose phi is 35 degrees. Okay. And bottom 4 meter is made of clay, which has C of 30 kilopascals. Okay. So here nothing is mentioned about C, and it is sandy soil, therefore C is 0. You should know. Whereas here nothing is mentioned about phi for the second soil. So you can assume that phi is 0. It is purely cohesive soil in saturated condition or so. So you can assume phi is 0. And then gamma is given for both sand and clay as 18 kilonewton per meter cube. You are required to find the total crust. So I want you to, basically use the formula. Okay. Sigma 1 equal to sigma 3 tan squared alpha plus 2c tan alpha. Or take this formula. If you can familiarly remember this, PA at any depth is equal to gamma z into Ka minus 2c into square root of Ka. For the top soil, Ka is equal to 1 minus sin phi by 1 plus sin phi. Phi is equal to 30 degrees. Therefore, it is 1 by 3 or 0.33. For the bottom soil, phi is 0. Automatically, Ka is equal to 0. I'm sorry, again, I made a mistake. Ka is equal to 1. It is no longer 0. So sorry for the mistake here. Ka is equal to 1 here. Okay. So at the top, Z is equal to 0. Therefore, pressure intensity is 0. That's what I have shown here. And at this location, point B, due to sand, pressure is equal to Ka gamma H. Ka is 0.33 into gamma is 18, what I have given, and H is given here 3 meters. Okay. So it is 18. So this is 3 meters only. Somewhere here I made a mistake. 8 meter, it is 6 meter high wall. Okay. So 3 meters only. Therefore, you get this value as 18. Then, when you take the effect of clay, please note on top you have a surcharge. Surcharge here is equal to weight of the sand. Weight of the sand is gamma times Z. Gamma is 18 and height is 3 meters, that is 54. Okay. So you apply here the same thing. So at point B, due to the effect of clay, or second layer, Pa is equal to, gamma Z, Z is 0. Therefore, this will vanish. Minus 2c times root of Ka. Ka is 1. Therefore, it is minus 2c. In addition, you have Q, that is the surcharge, which is equal to 54 kilonewton per meter squared. So 54 minus of this effect, C effect, 40, will give you 40 plus 14. Likewise, you find out at the bottom. At the bottom again, you apply this Z is equal to 3, and then you take the effect of cohesion. You find this value to be 68. So the distribution is of this kind. Total pressure is simply the area of this. So what is the area of this? You have this triangle, plus you have this square, rectangle, plus you have this triangle. When you take all these things, you will notice that area is equal to 150 kilonewton for 1 meter length, perpendicular to the wall. So this total will be 150, and that is what is given here. So many a times it is a multiple choice question you should be able to solve. So likewise, you have another question here from another GATE paper. So you have two soils here. First soil, top soil has gamma 15 kilonewton per meter squared. It's cohesion less, therefore C is 0. It has 5. Second soil has, again, it is cohesion less, C 0, but phi is 40 degrees. So you find out Ka for the first one, Ka for the second one. Please note, whenever phi is small, Ka is higher. So in a loose soil, in a soil which has less strength, the value of active thrust is more. So if you want to make the retaining wall have lesser thrust from this backfill soil, you need to densify it very well. So on the other hand, for denser soil, Ka2, is 0.217. Taking the same thing I have been able to arrive at the pressures at point A, B, and C. Point A, of course, is 0. Point B, due to the first soil, I have got this value, which is equal to 10. Due to the effect of surcharge on the second soil, I get this value of 6.51. And this is this rectangular portion. And then I get, for the effect of third soil, 8.68. Total pressure is simply the area of this, which is equal to area of this triangle plus area of this rectangle plus area of this triangle, which amounts to 31.7, which is also one of the solutions. And hence, I have many other problems. A 3-meter high earth retaining wall retains dry granular backfill of angle 30 degrees, unit weight 20 kilonewton per meter cube. If the wall is prevented from yielding, please note, that means, there is no strain allowed. This is for a situation of earth pressure at rest. You remember, in a cohesionless soil, earth pressure at rest is 1 minus sin phi. Okay, as per Jackie, who gave a research solution, K naught is equal to 1 minus sin phi. This simple solution we use, and hence, you need to find out how much is the total earth thrust. So here, instead of Ka, I have put K naught, and you find out that this value is equal to 45 kilonewton per meter square. You have another situation when you have a cohesionless soil. Whenever it is a cohesionless soil, at the time, you cut the soil, automatically there will be a tension here. But when you allow some time, sufficient time, slowly soil tries to settle down, and hence, whatever tension cracks which are developed, whatever tension is there, that will develop into crack, and then the tension will be let free. So before, at the time of construction, this is how the earth pressure will be. But after the tension cracks are developed, this value will become 0. You will have only the positive ones. This value I have tried to find out here using the same formulations, and this is the value you will have to put. So likewise, you have many different. A vertical cut is made, okay, and soil has some C, some phi, and then some gamma. What are the value? Ka and Kp are the active and passive pressure coefficients. What is the value of the what is the maximum depth you can allow without any support? I told you earlier, it is 2 times Z, where this is Z. You can easily calculate, and then A is going to be your solution. 4C by gamma into square root of Kp. So likewise, here you have a situation when you have the total pressure of magnitude equal to 20 times H. And this is going to cause a toppling moment equal to 20 times H into this value equal to 2 meters. Entire thing is resisted by the weight of the wall. This is a gravity retaining wall. So this 20H into 2 meters is countered by weight into this lever arm 2 meters. And you have to find out how much this weight should be. And you find out that value is equal to 120 kilonewton per kilonewtons per unit length. Yeah, you have a situation when you have a surcharge loading to be applied to counter the tension which is developed. So there is tension which is developed, and you have to balance. That value of tension is equal to 2C into square root of Ka, and that's what you will find out. Okay, this is the amount of surcharge to be applied. So and here you have a situation. Please note, a smooth rigid wall moves as shown in the sketch towards the fill. This is a passive situation, and when it moves, the major principal stress is always in the horizontal direction. So when it is in the horizontal direction, it is parallel to the wall face, or normal to the wall face, or oblique to the wall face. Naturally, it is perpendicular to the wall face. That is normal. So answer is B. So I can keep on talking about different methods, but I'll have to quickly go ahead. Coulomb's theory, has many of these assumptions. I'm going to just very quickly mention: homogeneous, isotropic, undeformable. That means, it is kind of that rupture plane is rigid plane, okay, and it has a plane surface. Failure is as a rigid one in translation only, and when the soil wedge is impending, that is at the time of failure, theory gives, two extreme cases: active and passive cases. The position and direction of the earth pressure is known. If the wall yields and the ruptures of the backfill soil takes place, soil wedge is torn off from the rest. That is, the entire soil wedge, it acts like a rigid body. It gets torn off from the rest of the soil. Friction is distributed uniformly. So you consider the wall friction here. For a rupture plane within the soil mass, as well as between the back of the wall and the soil, Newton's law of friction is valid. The back face is plane, backfill surface is plane, failure surface is a plane strain problem like in the other case. So you have the wall, which may be vertical or inclined, which may be rough also, and this is the wedge of soil which comes out. This wedge of soil has got the weight, and then this is the one which slips. This is the rupture surface, and hence, the shear strength in the soil holds it from slipping, and there is also the frictional resistance here. So you need to consider this weight. You need to consider the resultant force which is considered to be at an angle phi, and you need to consider the friction. Okay. Therefore, you have the main forces which are considered as weight, which has both magnitude and direction. Then the soil reaction, which is equal to phi with respect to normal of the failure surface. And then you have the passive earth thrust, as shown here, which also takes into account the wall friction, whose magnitude is not known, but the direction is known. So you can simply write the force triangle in which the weight, both magnitude and direction are known, and the reactions, the soil reaction as well as the active thrust, their directions are known, but the magnitude is not known. By simply drawing the force diagram, you'll be able to find R and PA. That's what the Coulomb's theory says. And main limitations are that, it does not satisfy the static equilibrium condition, which actually occurs in nature. Soil is considered as an ideal one. Error due to curvature of slips or plane is not considered properly. So there are some advantages, disadvantages of both the methods. And the friction between wall and soil is not considered in Rankine theory, whereas it is considered here in Coulomb's theory. Soil behind the wall is considered as a whole mass, a rigid body. Its deformations are not considered in both the cases, to be precise, but definitely not in Coulomb's theory. Lateral pressure is not limited to vertical walls only in Coulomb's theory. The resultant force is not necessarily parallel to the backfill surface because of the soil wall friction. On the other hand, in Rankine theory, resultant is considered to be parallel to the wall surface, perpendicular to the wall surface. Okay. So quickly, I go on to the other portions. Subsurface investigation is extremely important. I always keep saying that, we know quite a lot above ground, even in space. But what is happening below ground, we find it very difficult to understand. So unless you know what type of soil is there, what kind of strength, stiffness, and other properties soil imposes us at that depth, it is very difficult to build any geotechnical structure. So we have made different methods by which you do the subsurface investigation. And basically, by this investigation, you try to find out the properties of soil at different depths. And for doing that, you either require a field test, or these days we also use many non-destructive testing methods wherein you use subsurface investigation based on the wave theory. But to actually find out the properties more accurately, you try to do that, taking the soil samples from the field to the laboratory. And you have to see to it that the sample does not disturb the soil. Soil is a material which gets disturbed, which is very sensitive. And the amount of disturbance you give should be as minimum as possible. To understand the disturbance, you try to use a few parameters called area ratio, inside clearance and outside clearance with regard to the soil sampler. So these are given by the formula like this. I would like you to go through, and most of the times the area ratio is asked. So it is, if you see at the end, at the bottom, you have the inside diameter, you also have the outside diameter. So inside diameter I have called here D1, outside diameter I have called as D2. Area ratio is D2 squared minus D1 squared divided by, the inside one, D1 squared in percentage. There are a few important things you should know. Area ratio should be as small as possible. In general, it should be less than 25%. And if you want to sample very sensitive clays, it should be even less than 10%. Inside clearance should be between 1 and 3%. Outside clearance should be less than inside clearance. So the friction in the wall should be as minimum as possible, which means, you need to oil the surface to reduce the friction. Non-return valve permits easy and quick escape of water and air, which are not required, from the sample collection. So D1, D2, D3, D4, as explained, are mentioned here. So you may have questions like, degree of disturbance of sample collected by the sampler is expressed in terms of area ratio. If outer and inner diameters are DO and DI, the area ratio is given by, as I said, DO squared minus DI squared divided by DI squared into 100. That's what you have to write. Sometimes you may be given the values. DI is 38, DO is 44. Is it an acceptable one? You find out area ratio. In this case, area ratio is found to be 34%, which is much higher than what is acceptable, 25%. Therefore, it is not acceptable. So you have another question here. Which of the following statements is true for degree of disturbance of collected soil sample? You'll have to read this properly. Thinner the sampler wall, lower the degree of disturbance. Naturally, if you have a thin wall, the disturbance you create to the soil while collecting the sample will be less. So A is the correct answer. Here B, thicker the sample, then lower is the disturbance. Naturally B is ruled out. Thickness of the sampler wall and degree of disturbance are unrelated. No, this is also ruled out. Thickness of the wall really plays an important role. Degree of disturbance of collected sample is proportional to inner diameter of sampling tube, not necessarily inner diameter. It is proportional to the thickness. Therefore, A is the right answer. Then you have plate load test. And I wouldn't like to go very deep into it, but you know that this is one of the best field tests from the point of view of obtaining the bearing capacity as well as settlement of soil, because it exactly resembles the actual field condition. But then it has many difficulties also, many disadvantages also. You have a plate which replicates the behavior of a footing. Size of the plate is much smaller than that of the footing. You load this plate at the level of the foundation. And for loading, you either use reaction loading, or in this case, it is gravity loading. Gravity loading is done by putting some weight through maybe sandbags. Reaction loading is done through truss, like thing like this. And when you apply the load, you measure the corresponding settlement. So keep on applying more and more load and find out the settlement. So you plot a graph between load and settlement, something like this. And from this, you should be able to find out at what load the failure happens. Once soil fails, settlement continues forever. There may be some peak which is formed, and afterwards continuously settlement happens. On the other hand, you may not find peak at all. Settlement continues to happen with the load. So depending on the type of the shape of the load settlement curve, you may be able to explain what is the kind of failure the soil experiences under the load, under the footing, in this case under the plate. So you have a good method of doing the test, but there are some advantages and disadvantages of this. I'll try to read out very quickly the advantages and disadvantages. So the one of the biggest advantages is that it provides two important things. One is it considers the total failure, shear failure. The other one is it considers settlement. So it gives the allowable bearing pressure, taking into account both shear failure as well as settlement. And you don't have to extract sample because you do the test directly on the ground. And the loading is very similar to the load which you apply in the field. It is basically a quick method. You may have to do the test for about a week and get the analysis done, and that's it. Very quickly you can know the load carrying capacity of the ground. But then test results reflect, there are many disadvantages, reflect the behavior of the soil just below the plate. It is small sized one compared to the footing. So footing may be 5 times, 10 times bigger than the plate. So it only represents the behavior very close to the plate, but at deeper elevations, the soil may be very different. And if it is stronger, okay. If at deeper elevation, if the soil is weaker, we may be underestimating the bearing capacity. And because it is a short duration test done for a week or so, you may not be able to calculate the settlement. Size effect will be very pronounced in sandy soil, which is not considered. Generally, it's a cumbersome procedure. You have to do the test for a week in the field under, sometimes abnormal conditions. You don't have a controlled situation. So it's a tough environment in the field where you have to work. These are some disadvantages. Remember, the settlement is proportional to the width of the footing or the plate. In granular soil, you use this formula. In clay soil, you use this formula. Settlement of plate is proportional to width of the plate. Settlement of footing also is proportional to width of the footing. Therefore, by a direct value, relation or ratio, as shown by Terzaghi and Peck and later certified by many others. So SP by SF is always equal to BP by BF in clay soil, which is slightly different in sandy soil. So you have questions like, plate load test was conducted on clay soil with this dimension. Ultimate bearing capacity is found to be 180 kilopascal. And the ultimate bearing capacity of bigger, footing, 2 meter wide footing, same square footing, is how much? In the next class, I'll be teaching you this formula. This is the formula for ultimate bearing capacity, okay, of a square footing. And you will notice that because it is done at the ground level itself, this term will become 0. And this term also will vanish. So it is simply equal to this, which is a function of cohesion, and another term called NC, which is a function of phi. It is not a function of width of footing. Therefore, if 180 kilopascal is the ultimate bearing capacity of the plate, it is going to be the same for the footing also. So answer is B. So you have a situation here where the settlement of the plate is 2 millimeters, 0.3 meter by 0.3 meter plate is 2 millimeters. What will be the settlement of 2 meter wide square footing in clay soil? I showed you this equation, and use this equation and find out that for a small plate, when the width is small, the settlement is also small. And for a bigger footing, the settlement will be bigger, and it's found to be 13.33 millimeters. So you can rule out B automatically, it has to be bigger. And you also can rule out A because it has to be bigger. A and B are ruled out. And among these two, you will have to use this formula and find out this value. Standard penetration test, all of you should know, is one of the best known field tests for determining the properties of soil. What you determine here is N, standard penetration number. Okay, so it is determined at various depths, and for that you will have to make boreholes. Okay, so you make a clean borehole approximately 100 mm in diameter, but sometimes it could be less than that. You take a thick walled split spoon sampler, place it vertically in that borehole at the desired depth, and from the top you hammer using a hammer of weight 63.5 kgs and dropped from a height of 750 millimeters. You drop it, and then you find out the number of blows required for penetration of the sampler into the ground for every 150 millimeter length, totally 3 lengths. Then N is regarded as simply the number of blows required for penetration in the next 300 millimeters, second and third 150 mm, next to the first 150 millimeter penetration, which we call as seating drive. So N is equal to penetration for 300 mm after you achieve 150 mm penetration first. Okay, and you can correlate N with many properties of soil, like allowable bearing pressure, as seen here, given by Teng, relative density of soil. This is in the IS code IS 6403 as a function of phi. So you can directly relate N with phi, and you also you will have to apply some corrections. The major two corrections which we apply is, one is overburden pressure correction and the other one is dilatancy correction. Overburden pressure correction is equal to some coefficient correction for overburden pressure multiplied by the measured N value. And there are many people who have given this value of Cn. I have just taken Gibbs and Holt's value of Cn like this. You don't have to remember this, but somehow it is better if you remember this. Corrected value of N is 15 plus half into measured N minus 15, which is the effect of dilatancy in saturated cohesionless soils, saturated sandy soils. When it is dense, you will notice that measured value is more than the actual value. When the same soil is loose, you'll notice that measured value is much lower than the actual because of the existence of the pore water pressure. In one case it is positive, in the other case it is negative. So the test procedure I have written, which is very simple, you put the sampler vertically in the borehole, and from the top you hammer it using the hammer of weight 63.5 kgs dropped from 750 millimeter height. Some advantages, disadvantages. So test procedure is simple, and N can be correlated with many properties of soil, including dynamic properties. Samples which are collected in split spoon sampler can also be used for laboratory testing. Therefore, sample also is collected. It is a quick test, and you can determine N at intervals of 1 meter, sometimes even 0.5 meter in the borehole. What are the disadvantages? You are using dynamic load. The load is applied dynamically to determine static properties of soil. How accurate is it is a big question mark. You are not able to get the continuous recording. You require a borehole to be made, and that should be extended continuously. And sometimes if you come across a pebble in between, then you will notice that because of the encountering of pebble, N value will be much higher than actual case. Results depend on the equipment used and the people who handle equipment, which should not be the case. So some questions. If in saturated fine silty sand, measured N is 3, what will be the corrected value? The moment I say fine silty sand, you have to use this formula. Corrected value of N is equal to this. So this is 3. So 3 minus 15 is 12. Minus 12 by 2 is minus 6. 15 minus 6 is 9. So actual value is 3, but the measured value, the measured value is 3, but the actual value, corrected value will be 9. So in loose soil, you measure much lower than the actual value. Instead, if I say N is 33, fairly high, fairly dense soil, you'll notice that the corrected value will be lower than the measured one. So likewise, I consider here the effect of overburden pressure. And in this case, overburden pressure at the ground surface, if the measured N at the surface, ground surface, is 20, what is the corrected value of N? So at the surface, because of lack of confinement, you get always the value lower than the actual. So I have measured it as 20, and when I use that Bolt and Gibbs formula, you know that Cn is equal to 5, and this value will be 100. Corrected value will be 100 instead of 20 what you have got. You have 4 answers: more than 20, less than 20, equal to 20, and having no correction at all. Okay. Therefore, having no correction is a better answer. So automatically, the measured value at the surface is 20, but corrected value will always be greater than 20. So answer is A. Likewise, if it is at great depth, 50-meter depth, we may not be sometimes interested in it, unless the structure is very important. You will notice that the corrected value in this case is much smaller than the actual value. So the measured value is 20, but corrected value is 6.54. You remove the decimal point, because N is always a round number. So you can take the corrected value to be 6, much lower than 20. You also have cone penetration test, which is pretty much a more adopted test in countries, in European countries. So it's sometimes called Dutch cone penetration test also. So it is in our IS code. You're going to use a cone in this case, okay, along with a steel rod, and you use jacks for lowering it. You don't require a borehole to be made, and these are the equipment. This requires sophisticated equipment. So what you do here is that you have a steel tube and you have the cone with a rod here. So first you lower the cone for some distance, 8 centimeter. You find out the pressure required for penetrating that using jack, and you can have load cell or anything. You can find out what is the pressure required, and then lower the steel tube up to that point, 8 centimeters. Then lower both steel tube as well as the cone. So when you lower only the steel tube, you measure the resistance of the side, skin friction. When you push only the cone, you are going to measure the end bearing resistance. When you push both of them, you find out this as well as this. So you can separate out the effects of these. So you don't require a borehole, and you can continuously determine the value of the resistance in this manner. It's a static test, unlike SPT, and you can make continuous recording. You can use these relations with many of the soil properties, just like SPT. You can separate out skin friction from tip resistance. This test is preferred for soft clays. Some of the disadvantages: it is more tedious, the equipment is very expensive, results are likely to be affected by the speed of penetration, the test requires costly equipment, and this test requires costly equipment and more skilled labor. So I have about 15 minutes time. There has been a question from Sushil Kumar. What is a backfill? I just go back to the retaining wall. Okay. Please note, you have a retaining wall anywhere. I can take this figure only. This is the wall, and you have the soil on one side up to the top of the wall, soil on the other side up to the bottom. So here, this this is always called the front side of the wall. This is the rear side of the wall. The soil which is up to the top of the wall on the rear side, we call as backfill. It is the filled portion at the back of the wall. That is backfill. Okay. And this is the portion which is going to cause an earth pressure on the wall, both active as well as passive, and of course, earth pressure at rest. That's what we compute. I go back, I have 15 minutes, but I have plenty of things to cover. Maybe I may not be able to cover everything. And then, you have another question here. Group 1. Okay, this is a match the following. Group 1 enlists in situ field tests. And group 2 provides the parameters obtained from them. You match them. Pressure meter test. And what you find from, in addition to many things, Maynard's modulus. This is the Young's modulus of the soil. We have Maynard's pressure meter. Maynard is the one, who designed the pressure meter, and we call it as Maynard's modulus. And SCPT, that is static cone penetration test. What you determine is basically the skin resistance. You also determine, tip resistance, but here skin resistance. SPT, you always find N, number of blows. Vein shear test, you find out the undrained cohesion. Always vein shear test is conducted on in say clay soil, so you find out undrained cohesion. So automatically P is matched with 1, Q is matched with 3, R is matched with 2, and PQR, yes, this is yes, I forgot to mention, S is matched with 4, so answer is A. So I go further, stress distribution in soil. This is another very important topic. Soil has different levels of stresses due to its own weight. At the top, there is no weight on top of it, but when you go deeper and deeper, that amount of weight of soil will be exerting extra stress, which we call as geostatic stress. So the deeper you go, geostatic stresses keep increasing. On the other hand, there is also an additional stress which is applied due to the weight coming from some structure. It could be a dam, it could be a building. And that additional weight is also a stress, and the stress will be maximum at the point where it is applied. And when you go deeper and deeper, or when you go radially, the stress will decrease. Therefore, the total stress will be geostatic stress plus the stress due to the structure which you apply. And geostatic stress is simply, gamma times Z. For the vertical stress, horizontal stress will be K times vertical stress. K, when there is no extra strain, is K naught. When there is extra strain, it depends on whether it moves away from wall towards wall. And when the soil moves like that, so then, it creates active and passive situation. So we have to take them into account. And this is what is geostatic stress. But our interest is stress due to external load, which may be due to a structure, which may be due to a vehicle, which may be due to anything. Okay. And for that, Bouwsnik's theory is one of the most popular ones. He gave his theory based on theory of elasticity, assuming the soil to be elastic, continuous, and so on. And for different types of loadings. Please remember, for point load, this is the formula. If you have a point load Q, I'm sorry, here I took this figure from somewhere and equation from some other place. And I'll have to be first. I should stress disclaimer, mentioning that I have taken all these material from different sources. I acknowledge all those sources. The objective here is to share knowledge. So I don't take any. I don't have any claiming here. So this is a disclaimer which I want to mention here. So the vertical stress is what we determine, and horizontal stress will be K times the vertical stress. And in this case, vertical stress is equal to the magnitude of the point load, P here or Q here, both are same, divided by Z at any depth Z squared, into this coefficient, which is dependent on both z as well as the radial distance. I want you to remember this equation. And, as I said, this Q is mentioned here, and it is a function of the stress here is a function of depth z as well as the radial distance r as shown here. And these are some of the assumptions made in the Bosnick's theory. So soil mass is linear, elastic, homogeneous, isotropic, obeying Hooke's law. You neglect self-weight because you take effect of self-weight, as geostatic stress separately. There will be no change in the volume of the soil. Top surface is level and free surface, free from shear stress. So according to the Bosnick's theory for point load, we plot a stress contour like this, which we call as the isobar. This is the contour of some stress. You go deeper and deeper, that contour magnitude keeps on reducing. So when you move deeper or when you move radially, you notice that this stress keeps decreasing. And that is shown like this. At any horizontal level, stress below the point load will be maximum. You go radially away, the stress reduces. Similarly, in the vertical position, exactly below it, the stress will be close to infinity as per St. Venant's principle. But then, when you move radially and horizontally, you notice that, interestingly, the stress will be maximum at an angle beta given by 39 degrees 15 minutes. But either above this or below this, the stress will be smaller than that maximum value. You need to know this stress because when you put any structure, the total stress will be this plus geostatic stress. You should know whether the soil has got sufficient strength to bear this stress. So calculation of the stress due to this structure is very important. You have formulae for different types of loading, circular loading at the center, but at some depth Z is given by this formula. Likewise, you have the line load, a line load like this acting continuously in this direction, and you have the stresses, so vertical stress given by a formula here. You have a strip load, you have a vertical stress given by the formula here, and you also have rectangular load for which you can apply. So at least I want you to remember the Bosnick's expression for point load, because that will at least enhance your fundamentals of the stress at a point at some depth below the ground due to a superstructure which is applied. And this is called the pressure bulb. As I said, this represents the contour of equal stresses, and the stresses will be very high here. They reduce in this contour, they further reduce, and they reduce when you go deeper and radially outwards. And each one here is called the pressure bulb. Then you have contact pressure. Contact pressure is the pressure in the soil due to the contact with the structure, in this case, contact with the foundation. So the contact pressure will be non-uniform when the foundation is rigid. Most of the cases, foundations are rigid. On the other hand, in a flexible footing, contact pressure will be uniform. And when it is non-uniform, for two extreme cases, sandy soil, the contact pressure will be something like this. Clayey soils, it will be something like this. In sandy soil, contact pressure will be maximum at the center, minimum at the edges because of the confining effect. And in clayey soil, it is just the reverse because of the cohesion, mobilization of cohesion at the edges. There will be large amount of edge stresses compared to the stress at the center. So you have a few questions. Contact pressure and sediment distribution for a footing are shown here. Figure out what is the accurate statement. You notice here that contact pressure is not uniform, therefore the footing is rigid. And it is more at the center, less at the end, therefore it is granular soil. So A is the right answer, rigid footing in granular soil. It is not a flexible footing, not a flexible footing, and not a rigid footing in cohesive soil. Answer is A. Likewise here, you have a uniformly distributed line load of some intensity on the ground surface. And according to Bosnick's theory, the ratio of vertical stress at 2 meter and 4 meter is how much? Naturally, near the surface at 2 meter, the value is more than at the ends. And so therefore, answer should be, cannot be A, B, and it has to be C or D. And if you go back to the equation, say you take this equation only, which is simple, okay? When Z is 2 meters, the pressure will be Q by 2 squared, 4. When Z is 4 meters, the pressure will be Q by 16. Therefore, 4 times at 2 meters, it will be higher. So, between 2 and 4, the ratio here is 4. Answer is D. Same thing is asked here also, exactly similar. So, you have a pressure equal to sigma at some depth Z, at some radial distance. What is the pressure at half that depth? At half that radial distance, you will notice that the pressure is equal to 4 times sigma, which is also D. I quickly go to stability of slopes. When I cover the next lecture, I'll be talking about foundations. And if I have time and if I feel like talking more about, these topics, I'll probably cover a little of these. Slopes are very beautiful. We all want, slopes. We want hilly terrain. Okay. But they are not going to be beautiful always due to either external effects or due to the internal problems. They fail and cause a lot of problems economically and lot of casualties also. So slope is an exposed ground surface that stands in an angle with respect to horizontal, and it's our duty to maintain the slopes in stable condition. Slopes may be either man-made or natural. There are a lot of slope failures and landslides, even in Western Ghats, close to, our city, Mysore, or in the north, in Himalayas. It is a common feature, and we have had many fatalities due to the slope failures. These are some historical slope failures which have caused casualties of hundreds, thousands, 10,000s, even lakhs. So in this case, it is 2 lakh casualties. Slope failure triggered by earthquake. You have 70,000. So lot of casualties have happened because of continuous failure of slopes. So one of the duties of the engineers is to control that. So lot of causes are there for slope failure I have listed. Remember, earthquake or volcano is one natural cause. Heavy rains is another natural cause. Because of that, seepage happens. And there is also many man-made cause which we have to take into account. Any external load can definitely make the slope vulnerable. Even removal of trees can make the slope vulnerable and failure can happen. So slope failure can be broadly, either in terms of a slide, which is in a circular or curved mode, or a slide which is in the planar mode. So either you have rotational slides, which may be either circular or non-circular, or in a translatory mode. And you should know that here in slope stability analysis, you need to first find which is the most potential failure surface. And then you have to find out the forces which cause the failure or slip. And you should know which is the restoring force, that is the shear resistance, shear strength the soil has. And finally, our objective is to determine the factor of safety. Whenever factor of safety is 1 or more than 1, there will be no failure. On the other hand, whenever the factor of safety is close to 1 or less than 1, you always know that you are in for danger. So, factor of safety is shear strength divided by the shear stress which is applied. So, it is the restoring force divided by the disturbing force. So, you may have a slope which is infinite, or you also may have a slope which is finite. So, you call a slope as infinite when slope extends for great length in this direction and great depth in this direction. Okay. And it is the weight which is mainly responsible for the failure, which is resisted by the sheer strength of the ground. Okay. And you notice that factor of safety is always the ratio of tan phi by tan beta. What is tan phi? It is the strength. If you have a cohesionless soil having internal friction angle phi, then numerator is tan phi. Slope has an angle beta, then the denominator is tan beta. So you should know that factor of safety will be high when phi is greater than beta. And when beta is equal to phi, you are on the verge of failure. The factor of safety will be equal to 1. You also should know this situation. When the soil is in a submerged situation, there is seepage force, the water, which always acts, in the direction of gravity, and it reduces the strength, reduces the factor of safety. And this is the formula I want you to remember. Same, tan phi by tan beta. In addition, you need to add this one, submerged density divided by saturated density. So I would like you to remember this, and you have problems related to this, you can take that. And I have solved a few problems, simple ones, you can take them. So there are many, reading materials which are given in the net also. You can refer to them. And geotechnical engineering is a very beautiful subject. I would like you to master this, because any civil engineer should have a good knowledge about the ground which takes care of the structure. So I want you to study this very well. And today, I just would like to conclude that. So I try to very quickly talk about, these topics: soil stabilization, soil exploration, retaining wall, earth pressure theories, stability of slopes, and stress distribution. Wish you all the best and good luck for your preparation. I close my presentation now and hand over to the MC of the day, Professor Madhushri. Thank you, everybody.
Thank you, sir. Thank you so much for sharing your expertise to knowledge. So participants, we have come to the end of session 1. We'll have a 15 minutes break now. Please tune in back at 3:45 p.m. For the next session of day 8 on solid mechanics by Dr. Unisha. Thank you.